Every so often, a mysterious traveler enters our solar system. It glows faintly in the night sky, a frozen fragment from the deep past, and then disappears forever. But once in a while, one of these visitors turns out to be something far more extraordinary. In 2025, astronomers detected a faint, moving object in the southern sky. Its orbit wasn't bound to the sun. It came from interstellar space. This is Comet 3I Atlas, the third known interstellar object, and perhaps the most revealing one yet. Unlike typical comets, which loop around the sun in long, stretched ellipses, 3I Atlas follows a hyperbolic path, meaning it will visit once and never return. It's a piece of another solar system, born around another star billions of years ago. And it carries inside it the chemistry of a star and solar system different than our own. 3I Atlas was discovered by the Asteroid Terrestrial Impact Blast Alert System, or ATLAS, in July 2025. At first, it looked like any other distant comet, but astronomers quickly noticed something strange. Its speed was too high, its orbit too open. Calculations showed it was unbound from the sun's gravity, traveling nearly 60 kilometers per second, coming from the direction of the constellation Sculptor. It wasn't from the sun's family. It was a traveler from another system. Soon, the world's most powerful observatories, including James Webb Space Telescope, Hubble, and ALMA, turned their eyes toward it. Spectra from its faint, icy coma revealed a surprisingly high amount of carbon dioxide, far more than in most of our solar system comets. Whereas typical comets are dominated by water ice, 3I Atlas seems built from something colder, perhaps frozen carbon dioxide, carbon monoxide, and even exotic organics formed in deep, frigid regions far from its star. That clue alone told scientists it was born in a place very different from our early solar system. Every star system begins the same way, in a swirling disk of gas and dust around a newborn star. But not all disks are equal. Some form in rich, metal-heavy regions of the galaxy, seeded by recent supernovae. Others form in older, quieter clouds, where heavy elements are scarce and carbon dominates the chemistry. Those differences shape everything. The kinds of planets that form, the types of ices that condense, and even the colors of the comets that remain. In our solar system, comets from the Kuiper Belt and Oort cloud mostly contain water ice, mixed with carbon monoxide, methane, and dust grains rich in silicates. But 3I Atlas? It's much more carbon dioxide rich, suggesting it formed in a colder, darker, more distant region around its star, perhaps beyond the CO2 ice line, where even carbon dioxide could freeze solid. By studying its composition, scientists can reverse engineer the environment the comet came from. How much light did its star emit? How far was it from that star? What was the dust and gas made of? These are the same clues we use to understand planet formation, only this time from a world hundreds or even thousands of light years away. Now, here's where the story widens even further. Our solar system isn't fixed in space. We're orbiting the center of the Milky Way at about 230 kilometers per second, completing one full galactic circuit every 230 million years. In that time, we pass through different neighborhoods, dense spiral arms filled with newborn stars, quiet regions between the arms, and dusty molecular clouds rich in gas and debris. As we move, our solar system is constantly exposed to material drifting between the stars. Dust, gas, and sometimes entire comets, like 3I Atlas. Imagine the solar system as a ship sailing through a cosmic ocean. Every time we pass through a dense patch of interstellar matter, we pick up tiny grains of dust that originated around other stars. Some of that dust settles into our outer solar system, even into the Oort cloud, the vast, spherical swarm of comets surrounding the sun. Over billions of years, these encounters mix material from countless stars. It's entirely possible that some comets orbiting our sun today began life around other suns long ago, just as 3I Atlas began somewhere else before drifting our way. Stars, don't form in isolation. They're born in clusters with hundreds of siblings. When those stars pass near each other, their gravity can fling comets and asteroids into interstellar space. That's probably how 3I Atlas began its journey. Ejected billions of years ago, it's been wandering the galaxy ever since, until a chance encounter with our solar system finally let us catch a glimpse. For astronomers, this is a rare opportunity to understand a region of the galaxy we've never sampled directly. By examining its light with JWST's infrared instruments, they can measure the exact ratios of gases, water, carbon dioxide, carbon monoxide, and trace the dust's mineral makeup. The comet's high carbon dioxide-water ratio implies formation far from its parent star, in an environment colder and perhaps richer in carbon. That tells us about temperature, metallicity, and radiation in its birth disk. Already, early results suggest 3I Atlas might be older than our Sun, possibly more than 10 billion years old. It could have formed around a star from an earlier generation of the Milky Way, when the galaxy itself was still young. If that's true, this comet is not just from another star system, it's from another era of the galaxy. It carries within it the chemistry of a time when heavy elements were rare, and the first complex molecules were just forming. By studying it, we're literally looking back in galactic time. And as our solar system continues its journey through space, encounters like this may happen again. Astronomers now estimate that billions of interstellar comets drift through the Milky Way, possibly one or two passing through our neighborhood every year. Most are too faint to see, but with modern surveys and powerful telescopes, we're finally able to catch them. Each new object could tell a different story, a different star, a different chemistry, a different corner of the galaxy. Think about how quickly this field is growing. In 2017, we met Oumuamua, a strange, elongated rock that behaved unlike any comet we'd ever seen. In 2019, 2I Borisov arrived, a much more typical comet, but clearly interstellar in origin. And now, 3I Atlas, a bright, carbon dioxide-rich comet that challenges everything we thought we knew about how these icy bodies form. Each one with its own story to tell, of a star and solar system it left behind long ago. For scientists, 3I Atlas is more than an object of curiosity. It's a crucial data point in understanding how star systems build their worlds. By comparing it to solar system comets, we can see which chemical fingerprints are universal and which are unique to our local environment. It's like tasting water from different wells across the galaxy, each one flavored by the minerals of its home. Over the coming months, as 3I Atlas swings around the Sun and begins to fade, telescopes will record every possible detail: the brightness of its coma, the rate of gas release, even the shape of its tail. Then, long after it's gone, scientists will spend years analyzing the data, searching for clues about its origin and the star system that gave it birth. The discovery of 3I Atlas reminds us that our solar system is not an island. We are part of a galaxy filled with billions of suns, each forging and sharing material across space and time. The dust that formed our planets, the water in our oceans, even the molecules in our bodies, all may have once drifted between stars just like this comet. So, when our solar system crosses paths with a comet or an asteroid from interstellar space, we're not just watching an icy rock pass through. We're witnessing a messenger, a traveler from another world, carrying the story of a different sun. And as our solar system continues its long orbit through the Milky Way, we can only wonder, what other visitors are still out there, waiting to cross paths with our solar system?